Yeah, welcome to the third GPC climate seminar. And before we start, I just want to make some quick announcement about the GPC event at the March meeting. So, and here's a reminder that the abstract submission deadline for the March meeting is tomorrow, October 20th. So this year we are organizing 2 focus sessions in the March meeting, and this includes 6 invited talks by experts on several topics ranging from atmosphere, ocean, and ice. So please consider submit an abstract to one of our focus sessions. And yeah, deadline is tomorrow. And this year, GPC is also organizing a half-day tutorial session on Sunday, March 5th. And this is part of the APS March meeting. So the tutorial is intended for grad students, postdocs, and scientists who are interested in learning about the basics physics of climate. And you can register for our climate tutorial when you submit your APS abstract. In fact, Professor Tiffany Shaw is also one of our tutorial speakers. And finally, if you are a graduate student member of APS who is working on topics related to climate, or a GPC member who is less than 5 years out of PhD, please consider apply to these GPC awards. The recipient will receive up to $1,000, and that can be used for attending the March meeting. So to apply, you should submit a CV, your APS abstract for the contributed talk, and a summary of your work. So the deadline is not until December 11, and I'll put the links in the chat. Okay, so that's all I have. Yes, Pedro, you want to take it away?
Yes. Okay, great. Thank you for these exciting updates. So it's my pleasure to introduce today's speaker, Professor Tiffany Shaw from University of Chicago. Tiffany received her PhD in physics from University of Toronto in Canada. And after a year at the Grant Institute at NYU, she moved to Columbia University as an assistant professor of Earth and Environmental Sciences, Applied Physics, and Applied Mathematics. And after a few years, she moved to University of Chicago, where currently she is an associate professor of the geophysical sciences. Tiffany has been doing a lot of great work on understanding the dynamics of the climate system and the response of the climate system to climate change using one of the most valuable tools that we have, and that's the model hierarchy. And that's what Tiffany is going to talk about today. And for the great work that she has been doing, she has received many awards, just to name a few of them: the Sloan Research Fellowship, Packard Fellowship, NSF Career Award, and a number of awards from the American Geophysical Union. So we are very happy that Tiffany is here today to tell us about understanding climate change using model hierarchy. It's all yours, Tiffany.
Thank you. So thank you so much, Pedram, for the kind introduction, and for my colleagues for all their efforts to organize this wonderful seminar series to introduce the physics community to different aspects of climate change. And today I'm happy to be talking about uncovering the physics of climate change using the climate model hierarchy. But I thought I would start with my trajectory towards studying this subject, because I understand there are probably students in the audience who may want to know how people get into this. I certainly didn't start out with the idea that that was the focus I was going to pursue. So I was an undergraduate major in math and physics at the University of British Columbia in Canada, and I was very interested in those tools and the power of those tools to be able to explain the world around us. But I quickly realized I didn't want to explain the smallest of things or just prove things. And thankfully, I got connected to a professor in the math department interested in dynamical systems, who had read books by Childress on geophysical fluid dynamics. And so I was pointed toward the earth science department there, where I took a wonderful class in geophysical fluid dynamics. And I was essentially sold that I could use the tools that I love to understand things that I could see. That was really important to me. And after a couple of undergraduate research experiences to really see the value of research in this area, which I highly recommend to anyone who's interested In particular, there's existing programs like Leadership Alliance, which really will allow students to pursue these types of experiences and understand what research really means. After that, I became a PhD student at the University of Toronto, and this department in Canada is a department of physics that includes atmospheric physics. So I got to pursue my specific interest in the atmosphere, surrounded by, physics seminars in general. So that was quite valuable. And I did a thesis on Hamiltonian dynamics of a type of wave in geophysical fluid dynamics called gravity waves. And that was really valuable to combine theory and use simulations to show the impact of conserving momentum and energy for these wave motions. It has a very important impact on the surface climate as we simulate it in climate models. After that, I went to the Quran Institute, where I think really began my transition towards specifically studying climate physics. I started to think about moisture, which you'll see plays a very prominent role in my talk today. And I really enjoyed the colleagues there. It was a wonderful bridge for me to start thinking about climate in particular. And then finally, my career as a professor, I've had the opportunity to be in 2 wonderful departments and really have solidified my research direction to be the physics of climate change, both past and future. And hopefully you'll see that come out today. So let's get started with thinking about Earth's climate today. And as you'll see, I'm going to take a big picture approach because I think that's sort of very common in physics. And we can look at this beautiful satellite image from NASA and start to pick out the sort of major features of climate. And I'm going to focus on the latitudinal features because it's going to be easier for me to do that given the time constraints. So if we start at the equator, that's where most of the rain falls. Precipitation exceeds evaporation. As we move away from the equator in both hemispheres, we encounter the trade winds, which is the type of winds that blow from east to west. And this aided early navigation between Europe and the Americas. We also encounter a region that's relatively dry, where evaporation exceeds precipitation, where most of the world's deserts are found. And then as we move polar, the climate changes again, such as we have here in Chicago. On average, it's a very wet region. Precipitation exceeds evaporation, but our weather comes from the west, the so-called westerlies. So we have weather systems that come from the Pacific. So again, starting with this big picture of the latitudinal dependence, I think it's fair to say that we would like to understand, as we are currently experiencing anthropogenic climate change due to the burning of fossil fuels and the emission of CO2 gas, how these patterns will change, not only how they are changing and how they will change in the future. And so you can go online and ask this question, just like for weather forecasting, what will the climate of 2090 or 2100 look like? And there's an answer on Google. And here's an image of that climate from the Max Planck Institute of Meteorology. And this is the climate of 2090, the temperature. So these are isotherms relative to today. And then the main takeaway from this image is clear. You don't even have to see the contours to see that the isotherms are aligning with those contours. So land is warming a lot. And the deepest purple colors indicate that the maximum amount of warming is occurring over the Arctic. So of course, the question is, where does this information come from? We don't have observations of the future. Of course, if we did, we would use them. And the answer is that everything we know about future climate comes from climate physics. Okay, so we have essentially taken the climate system and represented it as a physical system. We have the conservation laws for momentum, mass, energy, water, and a beautiful book, although it is relatively old now, is this book called Physics of Climate. That's what encapsulates our knowledge in terms of the analytic equations. But we also have encapsulated our knowledge as a community into what we call climate model simulations. So that's what's shown on the right here. And what that involves is to take our analytic partial differential equations of the physical system, these conservation laws, and solve them numerically. Because if we want the most accurate projection of the future, over the entire globe, this is sort of, the unimportant approach that we need to take. But if we solve the equations numerically, we introduce a discretization, and that is this, taking the globe and tiling it with this horizontal and vertical grid. And so we know the physics and the solution at these grid points, But anything that's too small to be on the same length and time scale of our numerical integration represents a closure problem. Okay, so that is the physics that is small scales, such as clouds and convection, the turbulent exchange of heat and water between the atmosphere and the ocean, and the interaction of atmospheric gases with electromagnetic wave radiation is all what we call subgrid scale physics. And I think many of us may be familiar with the closure problem and turbulence. We need to represent those physics on the small scales in order to make an accurate prediction of the future. But that's not an easy problem. And so while climate models are an important tool in our toolkit, they include many uncertainties. So on the one hand, they have at their core this well-understood physics that forms the backbone of the integration. But as I've mentioned, this closure problem introduces structural and parameter uncertainty. We don't have, it's very hard to close these equations with only mean fields or this coarse information from this coarse grid. And we've come up with closures, but of course they're uncertain. Even if we did have, a perfect, theoretical closure, there would still be parameter uncertainty because those equations would depend on parameters, for example, with respect to clouds that we can't even observe. We cannot observe all aspects of clouds to have a perfect closure and have the information we need for the parameters that those would depend on. So that's one source of uncertainty. Another source of uncertainty in this climate model simulation is initial condition uncertainty. So the climate is a very noisy place, and we need to sample that noise as a function of different initial conditions, not unlike the weather forecasting problem. So we create ensembles is how we try to damp down the noise and amplify the signal. And then finally, there's boundary condition uncertainty. So this is so-called scenario uncertainty, where in order to integrate the climate into the future, we need to know how CO2, which is the dominant greenhouse gas in terms of future climate projections, how it will evolve. We know how it evolved in the past based on historical records, but we don't have that information for the future. So we have to choose different pathways, such as, the business as usual, that humans will continue to burn fossil fuels and emit CO2 like there's no problem. Or perhaps there's this situation where we, embrace green technology and we begin to curb our emissions. So that's the source of uncertainty there. So I think when we take those pieces together, it's fair to say that one thing you might consider is simulation doesn't equal understanding. We may be able to create those beautiful images like from the Max Planck Institute of the future climate in 2090. But when you combine that with all this uncertainty, I think there's a fair question is whether these are really trustworthy. And that's something that was articulated by Isaac Held several years ago. And I would argue that all is not lost here. What we need to endeavor, however, is to close this gap. Okay, such the point being that these simulations of a very complex system, which is Earth's climate, have emergent behavior in response to the CO2 increase, which if we strive to understand that from the underlying physics on the top right, then we can actually make progress and we can actually, advise policymakers with good understanding to take these projections seriously. So this is the objective, I think, of much of the work in climate physics today. And it seems like a big gap, but it turns out that for the first part of my talk, I'm hopefully going to convince you that there is a way forward here to close the gap. And that fundamentally relies on the groundbreaking work that was done by Suki Manabe and his colleagues, for which they were awarded part of the Nobel Prize in Physics in 2021. So this is Sukiro Manabe on the slide here, and his contribution was reliably predicting global warming. Of course, the question may be, how did he do that? I've just kind of cast this problem as this very big gap. So how did he reliably predict global warming? And my argument is going to be, as I'll show you by reviewing his work, that Manabe uncovered the physics of climate change by building a climate model hierarchy. So he basically took a very complex problem and took an approach that's very familiar to physicists, which is to say that he built a model of hierarchy, starting from the simplest possible model and adding complex physics as he went along. and trace through the emergent behaviors and responses from this complex system. And that's how he understood, and that's how he builds an understanding of climate change. So at the beginning, I'm going to review that work to hopefully make this statement clear. But obviously, in the context of quite a short seminar, I can't cover everything. And for those interested, here are some really great references for this work on the left in particular, the warming papers, and then other really useful books about climate change that you may want to look into if you're looking for additional information. So let's start with Manabe's work in 1967. This is one of my favorite papers, as you'll see. And the objective of this work was to predict the vertical structure of the temperature response to warming. So they essentially had reduced the dimensionality. They removed latitude and longitude. Think of it just as the global mean. And they're just looking at how temperature varies with altitude. And in this paper, they had a diagram representing their model, which is shown here. And I'm going to highlight for you that their model included these two parts I've already mentioned. It contained well understood physics. They were trying to predict temperature. The atmosphere was represented as an ideal gas. An ideal gas internal energy depends on temperature. So that's the bottom left. And in order to integrate that equation, they needed the diabatic forcing. Okay, so the non-conservative terms, one of which was dependent on phase changes of water vapor. So the other box in green on the top here manifested that dependence of water vapor on temperature, in particular the phase transition that happens as you go from vapor to liquid depends on the so-called Clausius-Clapeyron relation, which will feature prominently in my talk today. So they combined that well understood physics on the one hand with a lot of structural and parameter uncertainty. Now, in order to time step, they had to say something about how energy was transferred in this column, and there's two forms of energy transfer. One depends on electromagnetic wave radiation. And while we understand the black body physics quite well and the Stefan-Boltzmann law, we were still not representing the molecular interactions between the gases and the radiation. And also we were in this model accounting for the fact that there are clouds in the atmosphere. And that's quite a difficult problem, and they took the simplest approach to assume a cloud distribution with altitude. So that's a lot of uncertainty. They also had to deal with the transfer of energy due to convection. So convection transfers energy in the vertical due to the bulk movement of the fluid. And this is a closure problem. Convection was not represented. And so they took the simplest approach and they created an assumption of a relaxation toward an adiabat. And so they combined these two pieces, just as we do today, and they made the following prediction. Temperature is on the x-axis, altitude is on the y-axis. The three different lines show different concentrations of carbon dioxide, which is the primary greenhouse gas that we'll be interested in here in this talk from the perspective of predicting the climate response to anthropogenic forcing. And what I've done in the color coding, which was not in their figures, is extract for you visually the emergent temperature response, which is cooling in the above 15 kilometers and warming below 15 kilometers. So that's the so-called stratosphere above, troposphere below. And the beauty of this model is that they could well understand the physics that was controlling each of these responses. In the stratosphere, there's no convection, it's stably stratified. Temperature increases with height. So this is just a radiative cooling that's due to the dependence of long wave cooling on the CO2 itself. And in the troposphere, this warming below 15 kilometers is due to the combination of the greenhouse effect, which is predominantly radiative, and then also the adjustment of convection to the increase of CO2. So that was quite clear. They could understand what was going on in this model. But the beauty of this paper is they went further. They wanted to understand how the structural uncertainty of the parameters they were choosing, how that impacted their prediction of temperature. So here's a table from their paper where they focused on this increase from 300 to 600 parts per million by volume of CO2, a doubling. And in the middle column, they made an assumption that the water vapor would increase proportional to temperature. This is the so-called fixed relative humidity assumption, following the Clausius-Clapeyron relation. So warmer air holds more moisture. And if they took their average cloudiness, which they were prescribing based on the best available observations at the time, They predicted a warming of 2.36 degrees, okay, which stands right within the middle of our predictions, in 2022. Then they took a calculation where they had a clear sky. So they took the clouds out of the model and the warming was larger, which showcased the fact that clouds have an important role to play in determining the magnitude of warming in response to a doubling of CO2. And this is a problem that we continue, to work on as climate scientists in the present day. Then they did another amazing thing. They wanted to understand the role of moisture in particular, the moist physics. And so what they did was they created this third experiment with fixed absolute humidity, which is to say they fixed the humidity in the atmosphere, which they held the water vapor fixed. They didn't allow it to increase with the warming induced by CO2. And for their average cloudiness, the warming was about a degree less, which is a huge impact. And this shows they had an understanding then that the water vapor response to warming, the fact that warmer air holds more moisture is a huge controlling factor on the response of global warming at the surface. So that's where they started. And let's move now 10 years later, building off of that understanding, they increased the complexity of their model. Okay, now just like before, or we start with the vertical, now we add the dimension of latitude. This is a hemisphere now that actually has half land, half ocean, but the complexity is really in latitude. And here's the diagram of their model that I can once again, identify in green, the core physics that I understand well, the first law of thermodynamics. Now, because I have latitude, I have to deal with the fact in this model that the atmosphere moves. So that's governed by conservation of momentum, Newton's second law for this Newtonian system. And then we have conservation of water and energy balance at the surface. So that was combined again with structural and parameter uncertainty. We still have to deal with radiation and the fact that we have clouds in the atmosphere that interact with radiation. We still have to have a closure for convection, same kind of approach here with the relaxation to an adiabat. But then, because now we have a surface which goes all the way to the pole where the temperatures experience very little amount of sunlight, we can have ice and snow on the surface. And this introduces important aspects of surface hydrology, but also important aspects of the fact that a white surface, like a snow-covered or ice-covered surface, reflects a lot of sunlight, which is to say it has a high surface albedo. Albedo is just the magnitude and percentage of the amount of sunlight reflected. So it can be up to 80%, which is quite different than the ocean, which is very dark and only reflects, less than 10%, 7%. So they combined this new physics into their model. They integrated it forward in time to equilibrium. In one case with the standard value of CO2, the second case, they doubled CO2, just like 1967, and they took the difference. So this is the difference, standard, two times CO2 minus standard. And this is their prediction now of the temperature response as a function of latitude and altitude. So we've increased the dimensionality. And what's amazing, if you just step away big picture, is that above 15 kilometers again, there's really nothing has really changed. It's still a cooling. And what that's telling us is that the additional physics that we've added is not a leading, it's not playing a leading order role in determining that emergent response. In the stratosphere to leading order, it's just radiative cooling. Now in the troposphere, it's also just warming everywhere, but what I've highlighted for you in this colored contour is where the warming maximizes. And at the surface, there's this very unique and distinctive pattern of warming maximizing over the polar region over here. And then as we move toward the equator, the maximum warming is aloft. And again, because of the physics of this model, understanding this maximum surface warming, it could be easily tied to the surface hydrology that I spoke of before, where at the polar regions where it's very cold on average, where you have ice and snow, that is mostly reflecting the sunlight. When you warm the planet due to the CO2, you begin to melt that ice and snow, and you reveal below it a darker surface underneath, whether it's land or ocean, which tends to absorb more sunlight, which then would melt more ice and snow. And this leads to what we call a positive feedback, in particular, the ice and snow albedo feedback. So the warming is amplified over the pole as a consequence of this effect. And as we move toward the equator, the more warming is amplified aloft due to a different physical effect, which comes down to convection, something that was actually true in the 1967 model, but you couldn't see it because we weren't really looking at differences in that case. So what underlies this warming aloft is that at the surface near the equator, you have very warm and moist air. As you increase the temperature due to the CO2, the global mean warming, warmer air holds more moisture. And any air at the surface is ultimately moved upward through convection because the atmosphere is unstable. And so as that warm and moist air moves upward, it expands and it cools and it releases that latent heat aloft. So the warming induces the air to hold more moisture, and that more additional moisture is released aloft as additional latent heat of condensation, latent heat release. Okay, so finally, we increase dimensionality to something that looks more or less like realistic surface geography. Now we're in 1989, and there's no more diagram of the model. It's a short paper, but also, much more complicated. What they've added in terms of physics is obviously the full longitudinal dependence. You can see the realistic geography. But importantly, from the perspective of what we'll discuss, they've also added the physics of the ocean. The ocean can now move, okay? So it has its own conservation of energy and momentum. Having added all of that ocean physics, they also have to make a computation that's so-called transient or time dependent, because the ocean is very slow moving. And so they predicted here the surface temperature response to a transient increase of CO2, 1% per year, not a strict doubling. But what we're looking at is the difference in time when we do reach that doubling relative to that starting point or initial condition. So here's the temperature prediction, where if you just focus on the northern hemisphere and the region of maximum warming, it's occurring over the pole, in this case, the Arctic, just as the model in 1975 predicted. And again, this sort of tells us that all of this additional physics that we've added doesn't really have any kind of leading order role to play in controlling that polar amplified warming. However, if you look at the entire domain, what attracts your eye is this bullseye of cooling over the Southern Ocean and Antarctica. And we've never seen that before. Okay, this is global warming, but here is some cooling. So what underlies that? Well, the beauty of this approach is that now they can see the cooling, they can connect it to the physics they've added, which is the physics of the ocean, okay? So how we understand this today is that you, of course, warm the surface of the ocean, but superimposed on that, the ocean is moving. And how the ocean is moving around Antarctica and over the Southern Ocean is water is being moved upward toward the surface from the deep ocean, and the surface water is moving toward the equator. So the warming that happens at the surface layer is literally being advected toward the equator, and it's drawing up water from the deep ocean, which is colder. And so you've gotten this warming hole, or this transient cooling. But of course, it can't last forever, because eventually the ocean in its entirety warms, and this warming hole will go away. Okay, so that's the 1989 result. So now let's bring it all back together. The argument being that Manabe uncovered the physics of climate change using the climate model hierarchy. So again, starting in 1967, along this axis of physical complexity, we start with the simplest model, the simplest in the dimensional sense, just the vertical dependence, and also the simplest in the physical sense. We just have radiation and convection. And given those two things, we predict cooling aloft, warming below. And we also can use the model to understand the role of clouds, sensitivity to the clouds we've assumed, and also fundamentally understand the role that water vapor plays in controlling the amplitude of surface warming in response to this doubling of CO2. Then we add physical complexity, introducing the latitudinal dependence, the fact that the atmosphere moves and it conserves momentum. And what we can see is that in the stratosphere above 15 kilometers, that again, that physics has no clear role to play to leading order. It's still just radiative. And in the troposphere, we see some new emergent patterns that are tied over the pole to the surface hydrology and the ice albedo feedback. and then over the equator tied to the well-known amplified warming due to convective energy transfer. And then finally, adding the complexity of longitude and the ocean physics, we see that polar amplified warming still emerges, but only in the northern hemisphere. And we've got this warming hole that we tie to the fact that the ocean is moving as an entity, obeying its own physical laws. And so the amazing achievement here, I think, is that all of these signals were predicted, and they have subsequently been observed, even within the noise of observations. And so what Manabe has shown us is a path forward. How do we close this gap? We take a classic approach in physics. We strip down a complex system to its essential ingredients. We understand that system. We increase complexity. We learn something new about the response that we can connect to the physics we've added, and so on and so forth. So this is, I think, the beauty of the approach that can guide us toward to apply to any kind of signal that we see in these predictions. And so that's where I'm going to shift now to the second half of my talk, is following Manabe's footsteps, among many others, and focus in on a different signal. And these are just two popular science articles online telling us something about what's going to happen with the jet stream in the storms. On the one hand, some kind of polar shift, and then on the bottom here, that the tropical region as a climate zone is going to somehow expand. Now, of course, the question is, how do we know this? There's no observations of the future. And the answer, once again, is from climate physics and climate modeling. And the earliest known instance of this predicted polar shift comes from Manabe's work again. And this is from the 1975 paper, where he's looking at a different contour map now of kinetic energy in the atmosphere due to eddies, which are, in this case, deviations from a monthly time average. The main takeaway is this dipole as a function of latitude. This is a positive definite quantity, so there's a sense that about the maximum, which is right in between this dipole, we have this tendency of the storms and these eddies to shift poleward in response to a doubling of the carbon dioxide concentration. Now, 40 years later, we have many, many models. This is, the Intergovernmental Panel on Climate Change creates these coupled climate model intercomparisons. And each of these models represented with a number integrate and make a prediction of the future given some scenario of carbon dioxide, some time-dependent scenario of carbon dioxide indicated by these symbols. So what you're looking at here is what is going to happen in the future, 2080 to 2100 minus the present day. And the quantity being shown on the x-axis is the tropical circulation shift, which is, think about it very simply as just that nodal point of the surface winds, where we go from the trade winds, from blowing from east to west, to the westerlies blowing from west to east. So there's a nodal point of the winds where the wind is zero. Let's track that point, okay, and its position and latitude. And then on the y-axis, we're doing something similar, but we're tracking that point where we change from a dry region to a wet region. And all this figure shows is that these two things are highly correlated. Okay, correlation is not causation, but in particular in the red, which are the northern hemisphere values, they occupy this northeast quadrant, showing that it's a polar shift. The values are getting more positive, where the northern hemisphere Arctic is positive 90 degrees. And on the bottom left quadrant here, we have all negative values, which is the southern hemisphere, and Antarctica is minus 90 degrees. So again, a clear emergent behavior of a polar shift. We also see this in the jet stream. So here's a different paper, again, end of century minus the present day of the jet stream position in degrees latitude in different regions, southern hemisphere, North Atlantic, North Pacific. There's some scatter here, but on average, the means for sure are indicating a polar shift across different seasons. So of course, the question is why? What is the physics underlying this? Is it associated with something we understand well, the core of our climate simulations, or is it associated with something that we don't understand well, which is the structural parameter uncertainty? So our objective in the next little bit is to try to fill this gap between simulation and understanding for this particular signal. And I'm going to start off with some theory to kind of get at the very top end of this diagram, an intuition of why poleward, why not equatorward, even if we can't be quantitative about the magnitude, why poleward? And when you build a theory in climate, I think the thing that you're really needing is something that's, really robust and external, some kind of constraint. And I'm going to leverage the constraint of the so-called Clausius-Clapeyron relation, which is an upper limit on moisture. So here is the Clausius-Clapeyron relation. It's literally this blue line. It's like a phase curve separating water vapor on the bottom right from the liquid water on the top left. And the domain here is temperature on the x-axis and the water vapor, the saturated specific humidity, which is in the units of kilograms of water vapor per kilogram of dry air. So how we read this graph is we go to the x-axis. Let's pick off the Earth's global mean surface temperature, 285 Kelvin. We go up to the blue line, and that's the upper limit, the maximum amount of water vapor the air can hold at that temperature. So what happens if we warm the climate, which is what Minabe's work has shown us in the global mean? Let's envision a climate change that warms the planet by 4 Kelvin, where my climate change notation will be this capital delta. So I shift my arrow to the right. This is now the red arrow. I go up to the blue curve. Warmer air holds more moisture. Whoops. Now I can be quantitative about this, and I can say, well, how much? By how much? So I can take just a linearization of this exponential curve, like a Taylor series linearization, and it's 7% per Kelvin. That's the slope. So if I have a 4 Kelvin warming, I'm talking about 28% increase, which is quite a lot. But that really doesn't get us very far, I think, from a global mean perspective. That's really not the information we need for the winds, which is, I think, the objective here. Because the first thing you learn about when you take a course on geophysical fluid dynamics, which is the application of fluid dynamics to rotating stratified fluids like the atmosphere and the ocean, is for the atmosphere in particular, the force that gets the air to accelerate initially is a pressure gradient force, which is a force that depends on differences in pressure. Okay, so in particular, air will accelerate from high to low pressure, which can be also related to differences in density and temperature through the ideal gas law. So as the air does that, in order to achieve uniform motion, it's going to be subjected to another force that depends on motion, which is the so-called Coriolis force. And that Coriolis force deflects the air to the right in the northern hemisphere. And when we achieve this force balance, which we call, which underlies essentially why the westerlies are there to begin with, we have the air blowing from west to east aloft, and then at the surface from east to west, the so-called trade winds. Now, the reason I got into this is just to highlight for you that if we want to talk about the winds, really where we have to focus our attention is on the gradients, the differences in temperature, not the global mean temperature, which is what I just argued about and told you how it would change. So let's revisit this diagram with an eye toward gradients, not toward the global mean. So let's, instead of using global mean temperature, pick temperature for the pole and the equator. So that's my my values here, and the hypotenuse indicates that equator to pole gradient. It's really huge for the Earth's modern climate. And now the question is, what happens if we increase the temperature in a globally uniform way by 4 Kelvin? So here is my temperature change. I've moved both points 4 Kelvin to the right. And what this reveals in a very, I think, illustrative diagram way is that this gradient of moisture will increase, even if the temperature perturbation is uniform. So the equator to pole gradient increases under global warming. And now our interest is connecting this to the potential poleward shift that we see emerge in these complex simulations. So how do we make that connection? Well, we go to the theory as encapsulated by simple models that don't include all the physical terms, but they just include the dominant balances. Now, this is a theory of Carey-Emanuel's of the tropical circulation, and it connects the surface winds, which is one of our targets, to this moisture gradient. So the objective of this paper was to mathematically solve for the solution that represents this diagram, air rising where over a surface that's warm and moist, moving poleward, and sinking over a surface that's less warm and moist. And what he did was essentially combine those dominant force balances that I highlighted earlier in the horizontal, this balance between the Coriolis force and the pressure gradient force, and in the vertical, a balance between the vertical pressure gradient force and gravity. So I can't, of course, go on to the full derivation, but I can sort of give you the highlight of the result here, which is this equation for the east-west wind, little u sub s, so that's at the surface, depends on the following things. The temperature at the surface minus the temperature of the tropopause, because we've taken a vertical integration. The fact that the Earth rotates is in this f, which is the Coriolis parameter. It depends on Earth's rotation. The Earth's radius a multiplied by this partial derivative with respect to phi, where phi is latitude, of this quantity S sub s, which is the saturation entropy at the surface relative to a critical value. Now, the critical value is just what we need to exceed to get this overturning circulation. And so we've definitely exceeded that. Now, the question is, how will this, what does this tell us about climate change? So it turns out that the change of this surface wind under climate change, which is this capital delta US, the leading order term, the largest term in this dependence, comes from this latitudinal gradient. Now the numerator is also changing, but you can show through a back of the envelope calculation that it's a smaller contribution. And the denominator is not changing because that just depends on Earth's rotation and Earth's radius. And so this is an interesting term here, this change of the gradient of the saturation entropy, because saturation entropy depends on moisture. And it actually then can be analytically derived that this saturation entropy gradient change depends on the Clausius-Clapeyron relation. So this alpha delta Ts times, so that's 7% per Kelvin times the thing that we start with. So the moisture gradient we have today. Now the expectation, again, intuitively comes back to this picture. If we warm the climate uniformly, we steepen this gradient. We make this gradient stronger. And I should have said, why is this intuitive? Because I forgot. It's 28% if you have the 7% times 4 Kelvin, 28% of what you start with. So at the pole, you have very little water vapor in the air because it's very cold. So 28% is a very small increase, okay, times that small value. Whereas at the equator, it's 28% of what you start with, which is a lot of moisture in the air. So this is a much larger increase. So that's the intuition behind this steepening, which is of course also mathematically connected to the nonlinearity of the Clausius-Clapeyron relation. So we take that now and we substitute it into our wind change. Here it is again. And it turns out we get a sign definite response, which is always what we want to see if we're trying to infer some leading order behavior. And in particular, all of these prefactors, including the red, they're all positive. And then you've multiplied by the gradient of humidity at the surface, which is negative because you go from the equator where there's a lot of water vapor to the pole where there's none, and the pole is 90 degrees and the equator is 0 degrees latitude. So this is a negative definite change, which is to say that the trade winds get stronger. And at that nodal point where you go from trade winds to westerlies, you're essentially shifting that poleward. So that's the, I think, intuition of what this is providing us. Now, where does this ultimately connect in the bigger picture is to the fact that the water vapor is being evaporated from the surface. So underlying this connection is also the fact that evaporation as an upper bound can be related to the 7% per Kelvin increase dictated by this Clausius-Clapeyron relation. So we'll come back to that in a minute. So just as the saturation specific humidity increases, so does the evaporation gradient increases for the same reasons that I just outlined. So we've kind of back-ended our intuition at the top right, but we still have a lot of work to do to kind of fill in our understanding here. So the next place we're going to go is to follow Manabe and go to the modern climate model hierarchy, which is of course in color. And so the climate model hierarchy can be used to really target this moist physics and its importance. And so in the modern climate model hierarchy, we start on the left here, which is Manabe and Weatherald, 1967, the so-called radiative convective equilibrium. And then all the way on the right, you can think of this as the 1989 model of Stauffer, Manabe, and Weatherald, where we have everything in the kitchen sink, as sophisticated as we can make the model. The beauty is all of what's in between. So going from the radiative convective equilibrium, where it's just a surface that allows there to be a moist atmosphere, but it's a slab ocean, so there's no movement of the ocean, no physics of the ocean. We add rotation to go to an aquaplanet world, which has no land, and then we can add the complexity of land, and then we can add the complexity of the ocean physics and so on. And so if I'm trying to understand the role of this moist physics in the poleward shift, I need to go and start in a place where that model includes the essential physics. And I've outlined that moisture is important and rotation. So I'm going to target the aquaplanet. And the aquaplanet is a useful starting point, because when you take the aquaplanet and you increase the carbon dioxide concentration in the aquaplanet, a poleward shift emerges outside the region of noise, which is in gray. So the poleward shift is on the y-axis. For the tropical position, we see a poleward shift, so the expansion of the tropics, and for the mid-latitude position, which is the jet stream position, we also see a poleward shift. The aquaplanet is simple enough, it's not the simplest model, but it's simple enough that we can take this approach that Manabe and Weatherald took to try to understand the physics operating in this model, because we can control it and we can perform many simulations that we can't do with the most complex models. So we're going to systematically quantify the importance of different types of physics. The first is the dry atmosphere response, which is analogous to this fixed absolute humidity limit of Manabe and Weatherald. The atmosphere is moist, but we disable the ability of moisture to change. It does not respond to warming. That's like our null hypothesis, because we think moisture is important. So if we disable it, then we don't think there should be a polar shift. So we can test that. The next in magenta is this connection that we've been establishing between evaporation and saturation specific humidity, namely the Clausius-Clapeyron relation. So that's where we think the physics lies. That's we think is the most important. So we're going to have that on the table as well. But there's so much complexity in this simulation, there's other possibilities of what could be important, including the fact that evaporation depends on surface winds. So we allow ourselves to check that. That could potentially in this complex system play a dominant role. And then in addition, just like Manabe and Weatherald, we need to test the role of clouds and the way that clouds are behaving in this simulation to see if they contribute to the poleward shift. And we know clouds are an important source of structural and parameter uncertainty. So let's start by considering this null experiment, fixed absolute humidity. Well, good news, there's no polar shift. So that's already hinting at moisture is important. And we can go then to this mechanism we've outlined, the dependence of evaporation on saturation specific humidity through the Clausius-Clapeyron relation. We see that that does play a role in the polar shift. And more specifically, we can say, well, what if we follow our thought experiment and just impose a uniform global warming, which is what I really did in all of those diagrams. We see even a more prominent role for this gradient to induce a polar shift. We can also confirm that the surface wind-induced evaporation is not a leading order contribution, but clouds do play a role here, something that we've seen in many different papers. They, on their own, just through the fact they're warming the atmosphere, especially aloft, they introduce changes in temperature gradients, which can, in this case, also induce a poleward shift. So this is where, there is a source of structural and parameter uncertainty in this signal. So at this point, we've kind of filled in part of the hierarchy of models. And so just in the last few minutes, in the interest of time, I'm going to go all the way to the most complex models. Okay, ideally, you want to fill out the hierarchy, but let's just go to the end. And when we go to the end, the approach changes, because now we're dealing with a more statistical approach where we have a bunch of different climate models that are all very complex, but they've all done the same thing. They've all integrated the equations forward in time, given the same time-dependent CO2. And so now what we do is we look at all of those models and we say, okay, how much a poleward shift do they have or do they predict the end of the century relative to the present day? That's on the y-axis. relative to this evaporation contrast on the x-axis. Now, this is, of course, a statistical relationship, which is significant. And on its own, we would argue, correlation does not imply causation. But with the addition of this other aspects of the model hierarchy and the theory I presented, I think we start to think that we're onto something, and we are uncovering, some really emergent dominant control on this poleward shift through this moist physics and the change of the surface evaporation gradient. And we see similar behavior as we move into that was for the tropical region. We see similar behavior as we move into the region of the jet stream. Again, a significant relationship. So that's the main body of my talk. I want to summarize before I go to a few, I think, open questions that I think would be really useful when considering how valuable this approach is. So I'm going to just summarize by saying, I introduced to you sort of how do we understand climate physics. We need to bridge between the most complex simulations, which are used by policymakers to inform decisions about, what we should do as a society, to either adapt or mitigate these changes in response to anthropogenic climate change. But, simulation doesn't equal understanding. Arguably, we should only be advising policymakers on those signals that we truly understand. And that's on the top right. And so what we need is a way to bridge and to close this gap. And I argued in the first part of my talk that Manabe showed us a pathway for doing this by building a climate model hierarchy across a range of physical complexity, where we take an approach that's very, classic physics approach. We break down a complex system. We start with the simplest model, in the 1967 paper, which is radiation and convection, and we scale the physics up, and we trace through the emergent, in this case, temperature responses. And in each case, we can tie any new behavior to the new physics that we've added. I applied this approach to a different signal, this poleward shift. I started with trying to intuit the direction, why poleward, and I tied that to the Clausius-Clapeyron relation and the steepening of the moisture gradient using, simplified theories that, are simple because they throw out certain terms in our conservation laws. I used idealized simulations to kind of probe the physics operating when we have a lot of complexity and disable physics, just like Manabe and Weatherall did, and was convinced that there was definitely something important about the response of moisture for this circulation change. And then I used the state-of-the-art models to try to tease this out of a statistical correlation between the two things that I think are related physically based on these other lines of evidence. And so I want to just wrap up then by showing you that this, it's all very polished, but there's a lot of work to be done beyond what I've shown you. This is very much, I think, the focus of Manabe and my own work has been very much on the mean, the average values of the winds or the temperature. And one of the things that I think we need to think about, I'm going to highlight here. And so the first is clouds, because whether it was Manabe's work or my own work or many other papers in the literature, one of the things we continue to struggle with is the structural and parameter uncertainty associated with clouds. And the model hierarchy is a really great place, a really great tool to tackle this problem, but not in the hierarchy that I've been looking at today. In particular, I was looking at the hierarchy for the entire large-scale spherical geometry. There's a lot of exciting work going on to build a hierarchy for clouds that goes from simulating clouds in very small domains where you're faithfully representing the physics that are very local, so they're not on the spheres, scaling up to the full spherical, global cloud, global models that parameterize clouds. So that's one, I think, really exciting area that's ongoing. Another is to tailor this approach to say something about the really impactful events, the events that society is struggling with, trying to understand and needing to adapt to. And those we call extreme events. So large amplitude events that we are seeing, being able to use the model hierarchy to understand what do we expect should happen, what is the underlying physics that governs to leading order changes in the extreme events is another really important area that has had some nice work done around it, including for precipitation extremes, but there's a lot more to be done for both temperature, wind extremes, circulation extremes, you name it. And I think this approach of breaking down this complex problem and building up the intuition, starting with simplest physics, is a really valuable thing to be doing in this regard as well. And then finally, probably on the farthest end of where we might go in the next several decades is really scaling down the approach that I've applied today, which is for the largest scales of continental scale, jet stream scale, big things in the atmosphere, to start to understand much smaller scale features. And in particular, again, on this line of really high impact things, severe weather. And the interest is that some of these severe weather occurrences really depend on the large scale climate. And so there's a lot of potential there to understand better changes in future severe weather occurrence using the climate model hierarchy. And it's exciting to know that Professor Morgan O'Neill will be giving a talk in our seminar series in the new year. So I hope you'll all come back for that talk. It should be great. So on that note, I'll close here and happy to take any questions.
Okay, great. Thank you very much, Tiffany, for this fascinating talk. So I encourage everyone to enter their questions into the Q&A box. And while you are doing that, I just want to mention two things. All of these talks are recorded, and the recording are posted on the website, and you can access them there. And that next month, on November 16th, Professor John Wetlaufer from Yale University will talk about sea ice. So Tiffany, probably you can see the questions in the Q&A. There's already one there. So if you want to answer that, and then there might be more questions. And then Yao at the end wants to repeat those announcements again.
Okay, so I'll just, start by repeating the question from the chat. So, or unless the person wants to unmute themselves, or whatever works is fine with me.
I think maybe it would be, for the interest of time, if you just read the question and answer it, that might be the best.
Great. Okay, so the question is as follows. The first law of thermodynamics features prominently in GCMs. Is the second law of thermodynamics leveraged in GCMs at all? And so I'd say, the answer is yes. It's not one of the equations that we integrate, but it plays a fundamental role in how we interpret climate change. There is a new review article that Professor Morgan O'Neill, another reference to Morgan, they have a new review article about maximum entropy production and how one can interpret climate in some sense using that principle. But the second law of thermodynamics does, in some sense feature when we're talking about, adiabats and so on and so forth. So we do definitely use entropy, saturation entropy, as I referred to it in my talk, even though that may not be the equation that we're integrating in terms of the overall picture of the conservation laws that I painted in my talk.
Great. And I just posted that paper that Tiffany mentioned in the chat box. Albion?
Yeah, just sort of a more detailed question. In the full light model of Manavi with the longitudinal dependence, the warming hole looked concentrated in the specific sector of the Southern Ocean. Is that robust, and is there an understanding of that?
So that's a great question. The paper that I would point you to for the modern version of that figure would be Kyle Armour's paper in Nature Geoscience in 2016. I probably don't have the ability to drop it in the chat right now.
That's fine, I can look it up. Yeah.
It's a really great paper that is not only comparing the models, but also observations. And the sort of cooling is certainly more zonally symmetric, or certainly distributed more across longitudes in observations and in models than it is in Manavi's predictions. So, underlying that is probably just in the modern models a better representation of ocean physics, although it's still, of course, not perfect. But yeah, it's very prominent in observations, the Southern Ocean cooling.
And before I go, what's the time scale that the whole warming hole, the hole would sort of close up? I would imagine it'd be a bit long if it's based on large scale ocean circulation.
Yeah, it's like the ocean overturning time scale. So I don't know if there's a good reference for like someone who's computed it, but like hundreds to thousands of years. The models all vary a little bit in their Southern Ocean circulation, so that plays a role in the time scale estimate. But yeah, it's a good question to have a paper with that offhand, which I don't, but Yeah, maybe others in the audience do.
Okay, thanks.
Oh, okay. Here's a question from the Q&A. Does the aquaplanet model predict the increased waviness of the jet stream under global warming? Okay, so let's unpack that. Waviness can be measured different ways, but if you define it as that eddy kinetic energy, which was what I showed from Manabe's work, which I think is the kind of traditional way of doing it from the physics of climate approach, it does. Okay, so there's a polar shift, but if you integrate across that, you take, for example, integrate it from 20 degrees or 30 degrees to 70 degrees, the aquaplanet does have overall an increase of that eddy kinetic energy, which is a measure of waviness in it. Now, that aquaplanet does not have polar amplification. So, you know, for one reason, it didn't have ice and snow, and that's intuitively what I painted the physical picture of the connection of polar amplification to ice and snow. And so that changes things. So as you have a little bit of ice and snow in there, there's what we well know as kind of competing effects, and the net result can be a much smaller or even insignificant change in waviness if you do have polar amplification in addition. So we have, you know, a lot of colleagues have done very nice work to sort of establish that competing influence.
Great, thank you. Yao, would you like to quickly mention those updates again?
Oh yeah, let me close this.
Okay, yeah, let me just,
There we go.
how do I think I cannot share the screen. Maybe, okay, it should work now.
Yeah.
Yes.
Yeah, so I guess I just want to thank Tiffany again for just a really fascinating talk, and it's also very inspiring to learn you know, the climate science evolution, and also your story. And I guess I just want to quickly announce that make an announcement again that tomorrow is the deadline for the March meeting submission. And so we want to invite all APS members to consider submission to our 2 focus sessions. And we have 6 invited speakers from topics ranging from atmosphere, ocean, and ice. So please, yeah, consider the submission. And this year we have a new event. It's very exciting. So we have a half-day tutorial and March meeting, and Professor Tiffany Shaw will also be one of our tutorial speaker. So you should be able to register for our tutorial when you submit your abstract. And the finally is this award I want to draw your attention to. So if you're a student or early career scientist within 5 years of your PhD, please consider apply to these awards. You can receive $1,000 for attending the March meeting. And the deadline is December 11th. Okay, so that's all.
Great, thank you. So it seems that there's no other question in the Q&A. So again, Tiffany, thank you very much for this fantastic talk, both about your work and also like the about Manabe's papers. That was really fantastic. So thank you again, and we'll see you all next month for John Wetlaufer's talk. Thank you.
Great, thank you. Take care.
Thank you.